All right, does everybody have their beer in hand? All right, here we go. So, LSST is being built in Chile. We got that right. On the mountain Cerro Patron. We got that right. Hey, cheating! Scientists here. So, Cerro Patron is about 2,600 meters high. That's about 8,700 feet. It's in the desert in Chile, not too far from La Serena. Sorry? They do have snow in the desert. Not very much, just a little bit. And that's actually an important point. We tend to build telescopes on top of mountains in the desert because it's dry, and there's low humidity, and there aren't many clouds. So mountains are nice places because you get above a lot of the atmosphere, but building a telescope in, say, the North Cascades might not be such a good idea. Before we can build the telescope, we have to level the mountain, and that takes explosives, a lot of explosives. There were, I think, 6 or 7 rounds of blasting where they basically blew off the top chunk of the mountain and then dug in a big hole so that we could build a structure there. This is not what it looks like now. I'll show you what it looks like right now in just a moment. But LSST will be, this is the dome structure, a support building, and that little outrigger telescope, which will start operating pretty soon, which is a sky monitor, so that we can have very good, so that we can understand very well the features of the sky down there for calibration. And the design of this building is kind of unique. It's built specifically so that we don't have to move pieces of the telescope to other locations to fix them when we need to. And it's designed so that air can flow over it. It almost looks like you could put this in a wind tunnel and it would have a very nice, smooth path over it. And that's very intentional. In fact, it was designed to let the wind blow over it and blow through it to keep the air very stable so we don't get turbulence. This is what it looks like right now. This is a view that will be familiar to many of you who live around Seattle. It looks just like downtown. So that's the telescope. That's the beginning of the telescope enclosure there. This is the support building, and you can see the beginnings of that smooth shape taking form. In a little over a year, this structure will be mostly complete, and then we'll start loading in pieces of the telescope into it. And if you want, I will give a link at the end. There's actually a live webcam you can go to and watch the construction as it happens. So more about this special building. So I said it's designed to be very smooth, to let air flow over it. The dome itself is designed to be smooth and let air flow through it. You can see all of these holes, these louvers we can open and close to let the air blow through, to keep the air inside the dome at a very constant temperature and very stable. And we can cut this all away to see what it looks like on the inside. So LSST is unique in many ways. In particular, one of them is that we actually have our own lab for working on the mirror in the building. This means that we don't have to take the mirror off of the telescope, ship it down the mountain, drive it through the tunnel to someplace else to work on it. We can do it right on site. And that means we minimize our downtime. We can spend as much time as possible taking data. And you can see in here there's a giant elevator to move this 8.4 meter mirror down into the mirror lab, and we have all kinds of support equipment and repair equipment so that we basically have everything we need. We're self-sufficient there on the summit. And this is a relatively new thing. A lot of telescopes have to ship their parts elsewhere to get them repaired. So there inside the dome, you can see the telescope. So this is looking at just that dome. Here's a person for scale. So remember we said LSST is large. This is not the biggest telescope in the world, but it's comparable to basically all of the big optical telescopes today. But one thing you'll note about it is it's quite squat. So here's just the telescope. It's very short. It's compact, and that's intentional. So hanging off of the top there is the secondary mirror and the camera, which I'll tell you about in just a moment. And that's a couple of tons of weight up there on the top. And if those few tons of weight were further out, every time we moved the telescope, they would wobble around, and we'd have to wait for them to wobble around and settle before we could take a new image. So again, we're trying to maximize the amount of time we spend getting data, which means minimizing all of the time we spend waiting for things that other telescopes might have to wait for. So the primary mirror is down here, the secondary mirror is up there, and the imaging system's up there on top. And about this primary mirror, so this picture was shown before, 8.4 meters across. Some of you in the audience might recognize this guy in the sort of floral shirt. That's Željko Ivezic. He's a professor here at UW. I think this is the only time he was allowed to walk on the mirror. But so this was taken a few years ago after the mirror was cast. So they put it in a giant. They put a bunch of pieces of glass in a giant furnace, spin the furnace at a rate of a couple of times a minute, heat it up to a few thousand degrees, let the glass all melt into the shape that they want, and then give it several months to cool. And although this is the last time that most of these people were allowed to stand on the telescope, this was before it was figured, so it does not have the final perfect shape that it eventually had. Here you can see what it looks like after it got that shape. It's curved here in one way and curved there in another way. So people were allowed to walk on it here, and they are in fact painting it with blue paint. The blue paint is not what we use to detect things on the sky. It's a protective coating, because this was done just before they packaged the telescope into a big wooden shipping container to put it onto a truck to send it. It's currently in storage at the airport in Arizona, and in about a year and a half it's going to get loaded on a boat and shipped to Chile, where it will get loaded on another truck and driven up to the mountain. And one of the important things is that this telescope is 8.4 meters across for two big reasons. One, the mirror lab in Arizona has a furnace big enough for an 8.4 meter mirror. And two, there's actually a tunnel on the way to the mountain, and that's basically all that you can fit in that tunnel. This is not the sort of thing that you would want to airlift in. So once they've got this protective coating on it, it gets loaded up into a box and will eventually get mounted on the telescope. And you can see, now that they've got it coated with this protective coating, you can see that the inside of the mirror and the outside of the mirror have a different shape. And that's intentional. So light comes into the telescope, bounces off the primary, what we call the primary mirror, goes up to the secondary mirror, down to what in most other telescopes would be some mirror somewhere else, but in this case it's actually the inner part of the primary, and then up to the camera. And that's how we can keep the telescope so short and compact, is by folding the light like that. So I keep talking about this camera. So this is the camera. It's got three lenses. This is an exploded view of the camera, obviously. It's got three lenses, space for 5 filters, the detector you can see up there, and then all of the electronics on the back end. And I think we're coming up to another trivia question here. It's actually about the size of like a smart car. Right? So if we set this on the ground, it would come up to about here, and it's a couple of meters long, right? So about the size of a smart car. I see some debate going on back there. You can take it up with the judges if you have a problem. But there's all of this cooling equipment. So in the back here, the actual detector on the telescope is cooled to 100 degrees below 0 Celsius. And then all of the electronics are cooled separately because they put out a lot of heat themselves, and we have to keep this whole thing cool. So how do we detect things on the sky in different colors? So we have a filter wheel that lets us change the filter that we look through to see things on the sky. It takes a couple of minutes. This is about the right speed for how fast the filter wheel moves. It takes a couple of minutes to change. And remember, I said we keep trying to minimize downtime. We don't change the filter very often, because even just 2 minutes, that's 4 pictures we could have taken of the sky. So here we put the whole system together, and so you can see it's still quite compact. And there on the front is the detector showing some beautiful galaxy that we're going to detect, that we're going to see eventually. So let's talk about that detector for a minute. So there's the full moon on the detector. The image on the detector is about 7 full moons across, which is about 40 full moons in total. Yes, no, somebody got it, I'm sure. There's 189 4,000 by 4,000 pixel CCDs. Those are kind of like the CCDs that you find in your digital cameras or in your cell phones, but they're big. So every one of those little boxes is a CCD. So the CCDs are quite large. This is not, obviously not the detector itself, but a mock-up of it. And they're packaged into rafts, 3x3 rafts, 9 CCDs in a raft.
What's a CCD?
What's a CCD? Thank you. A CCD is a charged coupled device. It is a detector that every time a photon hits it, it records that photon. And you have them, if you have a cell phone with a camera in it, you may well have one. So we package them up so that if one of these CCDs breaks, we can pull out that whole raft and just put a replacement raft in. Much like Facebook or Google or Amazon, when one of their servers dies, they can just turn off the server, take it out, put a new one in. Exactly the same idea here. You take it out, you repair it somewhere else. Meanwhile, you put a new one in and you just keep going. So how do we put a telescope together? Well, it's really easy. Oops, back. How do we put a telescope together? No! Oh, yeah, try it. That's okay. I'll keep going. We'll just leave that one here. Never mind. There we go. I'll just talk it through. So the primary mirror goes at the back, the secondary mirror in the camera goes on the top, and the telescope goes into the enclosure. Pretty easy. Of course, this is going to take a few years and a lot of shipping of parts from all over the place. Some of these pieces are getting built in Germany, some of them are built in Chile, some of them are built in Arizona, so it's a multinational collaboration to put all of this together. So this here, once we have it all together, because of the design of the telescope, it lets us actually image the whole sky very quickly because we can move the telescope from place to place in just a couple of seconds, read out the detector in just 4 seconds, take another picture, move to the next spot on the sky, and keep going. So this is a simulation showing one way that LSST might observe the sky over time. These simulations are put together by a group here at UW. Is there anyone from the Sims team here? Oh, yes, over there. And the different colors you see on here are using different filters. So we make these simulations to model how LSST will actually observe over that 10-year time span. Finally, as David said, LSST is not just a telescope, it's a big computing infrastructure. So we're in the process of planning out the computers that we're going to buy in 3 or 4 years to actually process all of this data and manage this data. And this is the beginnings of our server room. These aren't the computers we're going to use when it actually starts, but these are the computers we're going to use to develop all of the tools that we need for when it gets going. And finally, LSST is a big group of people. It's a couple of hundred astronomers over 35 different institutions in 19 countries. This picture was taken just at the meeting where we got these fancy schmancy shirts in Tucson, and you might recognize a few people in there. For some reason they scheduled the meeting in August in Tucson. Maybe next time they can schedule it for August in Seattle and for January in Tucson. That might be better. So finally, I'll leave you with a couple of links. That shortened link there will take you straight to the webcam if you want to see what's going on the site right now. It's probably pretty dark there. The next link has a lot more details about the telescope site. And LSST is on Twitter and Facebook if you want to follow. They often post pictures of construction progress. I think right now, if you look at the Facebook page, there's a big picture of the enormous steel structure that holds the mirror in place. So thank you. Questions?
We'll just make sure to repeat the questions so everyone can hear, and you may have a glow stick chucked at you if you ask a question.
There's a question right here in the front.
Do I understand correctly, you're actually going to coat the mirror on the mountain?
That's correct.
Holy
so we
cow.
have the illuminizing lab that you can actually see it there. That illuminizing chamber is on the mountain. Yes.
Wow.
I think there was a question just over here.
I have a revealing question. Why do you build your own server rooms?
Why do we build our own server rooms? That is an excellent question. The kinds of servers, so the question was, why do we build our own server rooms? The kinds of servers and the kinds of processing that we do are quite different from the kinds of processing that, say, Amazon or Google do. We're not working with words, we're working with bits in an image. And so the particular specifications of the servers are actually quite different. More questions in the back. Over here somewhere. Yes, here. So the question was, are there plans to use neural networks to categorize the images? Absolutely. So I'm actually working on a project using machine learning to try to identify, and David's going to talk about this a little bit later, things that we find on the sky that are real versus things that we find that aren't. So yes, there absolutely, we have plans for, I mean, we're really sort of pushing the limits of what we can do with the data.
Is this replacing the Hubble?
Ah, good question. Is this replacing the Hubble? You'll see some slides about that later. The answer is no. They do different things. And I will go into some detail. I will answer that, I think, in full detail later. You were next?
So what's the effective focal length of this telescope?
Oh boy. Well, it's an 8 here you go. Do the math. It's an 8.4 meter mirror and it's f1.2.
1.2?
Yes, if you know cameras, f1.2 is really fast.
My goodness.
That is... Yeah, so the question is, who owns the telescope? That's complicated. The telescope itself is owned in part by Chile and in part by all of the members of the collaboration. The data will be owned by the public, so every year we're going to have a data release where you can get the data. And in fact, I think I'm stepping on some of David's points here. But yeah, so it's essentially owned by everyone who has contributed money to the construction. So I think it's 19 countries at the last count. You next.
Yes, after the 10-year period is over, what will the telescope do?
I don't know. So the question was, after the 10-year period is over, what will the telescope do? And the answer is, we don't know yet. Once we're done with taking this data, we might want to just keep going, or we might want to modify it to do something else. Fortunately, we've got about 15 years to figure that out. And I think I'll take one more question there in the back, and then we should move on.
How much did it cost? How much did it cost?
How much did it cost? You want to know what the trivia answer was. So who here has a pet? Yeah, have you bought costumes for your pets? So the total all-in cost for LSST is somewhere between $300,000 and $400,000, which is about how much people spend on pets. Million. That's the all-in cost of telescope, computers, my salary, their salary, all of it.
All right. Everybody please join me in thanking Dr. John Parejko for speaking to us.